We ended yesterday looking at the bonding between aluminum and sulfur. And what we saw was that you can't just write ALS because that compound doesn't exist. Instead, you had to write Al2S3 because that was the only way to make the valence electrons work. We moved dots all over the place. And the only way to have the octet good was to have this many of each thing. But then I ended class by showing you that we don't need to draw dots. We have a cheat we can use to figure out how many of each atom needs to be present to correctly write the formula in the way that it would exist. We're going to get good at it today, but here's the deal. Your job is not to walk away today feeling like a pro. You should walk out today feeling like you probably need more practice to understand all the stuff I'm about to show you. That would be normal, so that's good. Then we've got all next week to get really good at it because I'm about to show you a lot of stuff. Ionic nomenclature. The word nomenclature is a fancy word for naming. Our whole point today is to take ionic compounds, a plus bonding with a minus, and figure out the ways to write these formulas. Let me show you what I mean. Make sure you write every ounce of what I write. I'm going to write the same thing. You're fine. I've got to do it lower. My computer people can't see. That says lithium nitride. Our job is to write down the formula for lithium nitride. But there's only one right way to write it. First, we need symbols. What's the symbol for lithium? Li. Nitride. Now look here. Look. You see that I right there? Here's what I want you to do. On your periodic table, on your periodic table, where you have the negative numbers written, the negative numbers written above 16, 17, and 18, I want you to write I'd really big, right here. Above the -3, -2, -1, that whole chunk of area, I want you to write I'd really big right there. Whenever you see a word ending in "ide," it's almost always referring to an element over in that area, over in columns 15, 16, and 17. What element do you think nitride really is? It's just nitrogen. Now, there's exceptions to that because there's exceptions to all my rules, and I'll show you it in a few examples. But almost all the time, ide is on the periodic table. What is lithium's predicted charge? It's +1. Does everybody see where I'm getting that? Does everyone see where +1 is? Because it's vital. Don't fall behind. You'll snowball and never catch back up. Everyone see why lithium is +1? Yeah. What about nitrogen? What's his predicted charge? -3. Now, the fact that one's positive and one is negative is what makes it ionic. It's what makes all these rules apply. They all will be today, but I wanted to point that out. But see that plus and minus? We don't really need that for the skill. But it does verify that it's an ionic compound. As I showed you at the end of yesterday, our cheat allows us to do what's called a crisscross to assign subscripts, the little numbers, to the elements. And when you crisscross these, what number did I crisscross the lithium? I gave them a 3, just follow the arrow. And what did I crisscross the nitrogen? A 1. Don't write the 1. We don't show 1s. Lack of a number is a 1. Think about water. All right, if you look at water, this means that I have 2 hydrogens and 1 oxygen. All right, we don't show 1s. There's the answer. Now, just to reconnect, don't draw what I'm about to draw, but to reconnect what the heck that just was. This says that when lithium and nitrogen are going to bond together, you need one nitrogen. He's got 5 valence electrons. And you need 3 lithiums. They each have 1 valence electron. And by doing this, I get 3 naked lithiums and 1 totally clothed nitrogen. 3 lithiums and 1 nitrogen. But we're not drawing dots anymore. I just wanted to reiterate that that's really what's happening here. Write this down. Potassium oxide, it's always the same sequence of steps. I need symbols, I need the charges of those symbols, and then I need to crisscross them. What's the charge of potassium? I'm sorry, what's the symbol of potassium? Okay. What's the symbol of oxide? It's just O. Remember, if it ends in IDE, it's usually an element from the periodic table. That is just oxygen. What is potassium's oxidation state, its predicted charge? It's +1. All right, what is oxygen's oxidation state? -2. All right, a plus and a minus. It's ionic. Awesome. Crisscross. K2O. Perfect. This is the only correct way to write potassium oxide. And the reason I say it like that is on the computer day, I'll say that and they'll be like, oh, but I wrote it like this. Is that okay? No, 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 no. There's only one right way to do any of these. That is potassium oxide. You try one. No, no, no. We're going to do radium sulfide. Radium sulfide. See if you can get that answer. Radium is Ra. Sulfide is just sulfur. Radium has a predicted charge of +2. Sulfur has a predicted charge of -2. And now look here because you probably got it wrong. If you wrote Ra2S2, then you've listened to everything I've said, but I set you up for failure. Cross that out. That's not the right answer, because here comes the first of a bunch of different rules. If those two numbers are the same, 1 and 1, 2 and 2, 3 and 3, 99 and 99, that won't happen. Then you crisscross nothing. And just take whatever you've written as the symbols and put them together. Now, if you're wondering why, remember, this is a cheat that I'm showing you. If we go back to the dots, I can show you why very easily. Radium has 2 valence electrons. Sulfur has 6. And it should suddenly be very obvious why you only need one of each of them to move dots around and make everybody stable. But this is always true when the two numbers are the same. Rubidium hydroxide. I have another exception in this, so make sure you're not zoning out on me in any way. What's the symbol for rubidium? RB, right? They make good roast beef sandwiches. Joke's always funny. Hydroxide, though, breaks my IDE rule. Hydroxide is sometimes misinterpreted as hydrogen, but that would be hydride. Hydroxide is going to be your first introduction to the polyatomic list. Look at your list. Again, almost all the time, IDE means the negative area of the periodic table, except for hydroxide and cyanide. Those are the only two guys on this list that end in I. What's the symbol for hydroxide? It's OH. OH. Now, if you were memorizing these, like I really think you should, then when you saw hydroxide, you'd know right away it was OH, and you wouldn't have to worry about misinterpreting it as something different. But you'll have that list. Hydroxide is OH. Now, even though we're going to start using these polyatomic ions, and by the way, if you look at them, all they are it's one word, and the formula is multiple elements. But our process here won't change. What's the oxidation state of rubidium? It's +1. What's the oxidation state of hydroxide? It's -1. It's right there on there. If you look at the polyatomic list, it's right there. It tells you that he is -1. What's going to happen? Hey, they're both the same number. We don't crisscross when they're the same number. We just jam the symbols together. Rubidium hydroxide. What's that? You want more crazy rules? Let's add some more rules to this. Write this down. Aluminum sulfate. What is the symbol for aluminum? Al. Sulfate. Now, hey, when you see things ending in ate and ite, that's definitely from the polyatomic list always. What is sulfate? He's SO4. Now, look here. I have a little soapbox about my sulfate here. Look. That little 4 right there will drive some of you crazy. Because when you start crisscrossing and doing stuff, you'll sometimes think that 4 needs to change. No, no, no. Sulfate is SO4. No matter what you end up saying your answer is, make sure that sulfate is a part of it. SO4 needs to be in whatever formula you're about to tell me aluminum sulfate is. Don't mess with that 4. But let's go through our steps. Aluminum has a predicted charge of +3. Right? Everybody sees that? Yeah? Don't not see that. What about sulfate? What's his oxidation state? -2. Are we going to crisscross those numbers? Yes. We are. They're different. Here we go. The 2 to go there. I want the tree to go there. All right, let's write it. Aluminum. Got a 2. Sulfate, which is SO4. Now watch. I'm going to show you the answer and then totally explain it. We have an introduction of a brand new feature. Let me explain. The final answer is Al2 parentheses SO4 parentheses 3. If you look on the back of your polyatomic list, you will see a sheet that has a wordy version of all of the exceptions. So if you like the notes, here it is. That's for you. Don't look at it right now, but it exists. 2 things about parentheses. Look here. First off, the only things that can get parentheses are these guys. Don't ever put parentheses around like just aluminum. All right? The only time that you can put parentheses around anything is if that thing is a polyatomic ion. But here's the rule. God, there's only one time. It's so easy. Only one time you need parentheses. If a number bigger than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, is being crossed to anything on the polyatomic list, then you put parentheses around that item. Listen to that again, because if you can just learn that one sentence, then you're good to go. If a number bigger than 1 is crisscrossed to a polyatomic ion, you put parentheses around that polyatomic ion. That's the only time it happens. Let's keep going. Exactly right. Write this down. barium hydroxide. What's the symbol for barium? Ba. Hydroxide. We've used him before. What's his symbol? OH, right? He's one of the few, the exception ides. All right, he's an ide on the polyatomic list. What is barium's oxidation state? +2. Hydroxides, -1. The numbers are different, so we will crisscross. I want the 1 to go there. I want the 2 to go here. We don't show 1, so barium is good like that. And then what happens? No. Parentheses. Look at the rule. It's the one-sentence rule. Is that number bigger than 1? Yep. Is it being crossed to a polyatomic ion? That's the only time you do need parentheses. Doesn't matter if the polyatomic ion has a subscript or not. Don't get caught up on that. OH with parentheses around it, and then give it the number you were supposed to give it. Questions so far? We're doing all right? We feel okay about this? You try a couple. I want you to do strontium phosphate by yourself and calcium dichromate. If you need any help at all, call me over. I'm very happy to help you. The moment something that I write doesn't match what you wrote, scream at me. And please put your electronics down. See, now that's on the video forever. Strontium is SR. Phosphate is PO4. Strontium has a predicted charge of +2. Phosphate, a predicted charge of -3. The numbers are different. We're giving strontium a 3, and we're giving a number bigger than 1 to a polyatomic ion. So I'm going to put PO4 in parentheses, and then I'll give him that number. Calcium is Ca. Dichromate's kind of funky. Cr2O7. Calcium's oxidation state is +2. Dichromate's oxidation state is -2. They're the same number, so I will not crisscross anything and just push the formulas together. Anybody get a different answer? Iron oxide. Don't try to work ahead of me, you can't. Iron symbol is Fe. Oxide's symbol is what? Just an O. Ide from the periodic table. Iron's charge is a problem. If you go and look at the periodic table, you'll see that iron doesn't have a charge written above them, and here's why. Iron can have a charge of +1, +2, or +3. It depends on which iron I'm talking about here. And I could be talking about any of them. Last unit, we learned that the transition metals that don't have constant charges, because they can have different charges, had a unique thing we would use to show their charge. What was that thing? It was Roman numerals. You see the way this is written right here? I'll never write it like that. This is incorrect. That doesn't exist. Instead, it'll look something like this. Fix it on your paper. All right, scoot that between there if you can, or just rewrite it, because this is a real example. Now, look here. Traditionally, chemistry students think that Roman numeral problems are the hardest ones. Sometimes they just flat out skip them when they run into them. I'm here to tell you that Roman numeral problems are the easiest ones. They're the ones that you want to hope I give you the most of, because these are the only ones that you don't have to go look other places for charges. On every problem before this one, you always had to go to either the periodic table or the polyatomic list to find the charge of everything. Not here. What's the charge of this iron? It's +3. And now we're done using the Roman numeral. Please don't fall under the impression that Roman numerals are something really, really weird. All they do is tell you the charge of him. And then we go on. What's oxygen's charge? -2. The numbers are different. Crisscross. This is iron 3 oxide. That's really how you say it. Iron 3 oxide. You want to see the wrong answer that y'all love? This next thing I'm going to write will always be one of the answer choices for this problem. Watch, watch, watch. Iron 3 oxide. And y'all will magnetate? That's not a word. Y'all will be drawn to that awful, awful answer. All right? The irony, get it? Irony. The irony is that that 3 that you want to put in that spot actually ends up on the other guy, not on iron. Do another one. Write this down. Nickel 1 nitride. The symbol for nickel is Ni. The symbol for nitride is just N. It's ide. It's an element. What's the charge of nickel here? +1. All right, and for those of y'all like, how did you know that? Right there. There he is. That's all he does. The Roman numeral tells you his charge, and that does nothing different. 1. What's nitrogen's charge? -3. The numbers are different. Crisscross. What's the final formula? Ni3N. Nickel 1 nitride. You do a couple. solve both of those. Let me know if I can help you. Is it? The question was, is that a 4? What Roman numeral is that? It is a 4. Make sure you know your Roman numerals. I will not answer that question when you call me over during your test. I was just accused of not giving you enough information for the second one. If you're still working on the first one, keep working. But I was asked, why doesn't zinc have a Roman numeral? I have a plot twist for you. An exciting little twist. Look here on your polyatomic sheet, down in the bottom left, or bottom right, sorry. You'll see a surprise down there. Now finish that problem. The symbol for cobalt is CO. The symbol for nitrite, be careful with nitrite and nitrate and sulfate and sulfite. Nitrite is NO2. Cobalt has a predicted charge in this case of +4. Nitrite is -1 because your polyatomic list says so. The numbers are different. And a number bigger than 1 is being crisscrossed to a polyatomic. So we got a bunch of stuff going on here. That's what I get as an answer. Now, zinc. Let's talk about zinc real quick. Look here, look here. Remember, the whole reason that Roman numerals exist is because transition metals have different charges. All right? Cobalt is not always 4. Sometimes he's 3. In this case, I said I want him to be 4 because in nature we have found those different cobalts. But there's 3 transition metals that we haven't found more than one version of. Zinc, cadmium, and silver. All right, the ones that are sitting there in the bottom right-hand corner. They're just like these other guys that live in the columns where there's a constant charge. Oxygen is always -2, the same way that zinc is always +2. You need to memorize those 3. Zinc, cadmium, and silver, +2, +2, +1. Carbonate is CO3 with a charge of -2 on the polyatomic list. They're both 2s, so you will not crisscross anything. ZnCO3 should have been the answer there. Questions? Here's the bad news. It took me almost, don't put your stuff away, we're totally not done. It took me almost the whole period to show you all the rules for writing formulas. Again, if you feel okay about them, then you're normal. You shouldn't feel perfect. But this is only half of what you're expected to do, because you've got to be able to go the other direction. Meaning, if I give you this, you need to be able to write the words. Now, that's the bad news. The good news is that it is much easier to write the names than it is to write the formulas. So much that I'm going to show you how to do it right now. Write this down. And put a divider in your notes because this is something different. Still ionic nomenclature. But we're going to go the other direction. Writing the names is very simple because as long as you know where the compound divides in half, then you just get to name both parts. Like, watch. If you wrote this down, I want you to literally do that in your notes. If you look at our previous examples, it's always a two-word name describing a single compound. So we just need the two words. What do I call him? Sodium. But be careful on that second word. The second word is going to end in either "ide," "ate," or "ite." The ides come from the periodic table, except for hydroxide and cyanide. The ates and ites all come from the polyatomic list. See him? He's on the periodic table, not the polyatomic list, so we want to call him chloride. Sodium chloride. Let's do another one. Chloride, because chlorine is on the periodic table. Sodium chloride. Chlorite is ClO2, as you can verify on the polyatomic. The trick is, where do you divide them in half? But again, it's very simple. Watch me divide them in half. How do you say the RB? Rubidium. How do you say the P? Don't call it phosphorus, that's no good. It can't end in OS. Phosphide. This is rubidium phosphide. Notice how that 3 didn't matter. The 3 had to be there because these are the respective charges of those elements. So when they crisscross, that 3 appears. But the 3 didn't matter for naming it. That's why this is so much easier. Sir, will the numbers ever matter? Yes. When there's a polyatomic in there, which is why you should memorize them. Look at this last example of the day. Here's our last example. If you have your polyatomic ions memorized, or at least if you're super familiar with them, which over the next week, while we really practice this ridiculously, you're going to get familiar with them. But on this one, where you divide it could be a little trickier. Where am I going to divide it? Right there. And again, you're just going to name what you see. What is NH4? It's ammonium. What is ClO4? It's perchlorate. Again, you shouldn't be a pro yet. I'm going to get you there next week.